All right. Hello again and welcome back. This is part two of our chapter three lecture, and we are picking this up on slide 19. Okay. So first of all, when we are mixing an acid and a base, this reaction is known as neutralization because when we're done, our solution is neither acidic nor basic. Okay, so this is an example of so the net ionic equation for the neutralization of a strong acid and a strong base creates water. Okay. Now, below here, we're going to show the reaction between sulfuric acid and sodium hydroxide. Okay. So first of all, sulfuric acid, H2SO4, and strong acids and bases are always liquid. So we have H2SO4 and sodium hydroxide, which is NaOH, and you can find these on those lists that you made during part one. And when we bring these together, we always make water. So that's the first thing that we're going to make. Now, notice here that you have two protons and one hydroxide. So if you have two protons, that's an H plus and an H plus, that means that you need two hydroxides in there as well. And that means that you will make two waters. Okay, so here we have one H2SO4 and two sodium hydroxides make two waters. And then we're going to go ahead and finish it up by taking the Na plus from our sodium hydroxide and the SO4 2 minus from our sulfuric acid and making Na2SO4. Now, the state for H2O is liquid, and for Na2SO4, it is going to be aqueous. Okay. Now, if we want to, we can go ahead and I'm just going to get rid of these so that we can just look specifically at what we're looking at. Okay. So now what we have our complete ionic. There we go. So now we have a complete ionic equation. And in our complete ionic equation, remember, what we're going to be doing here is we're going to be breaking it up. So here we have one H2, so we have two protons, and they're aqueous because they're aqueous here. And we have one sulfate ion, and we have two sodium ions. And I'm just bringing this straight down from my molecular equation, but I'm breaking it up. And two hydroxide ions. And when I balance it, so notice that the water is together. It's not aqueous. So that has to stay together. And then I have two sodium ions here. Oh, I have run out of room. So I also have one sulfate ion below. Okay. All right. And now, so let's just kind of take a quick moment here. You can see these two waters, that stays the same because they don't get broken up. Now let's take a look at what's actually happening here. So you'll notice that our two H pluses and our two OH minuses are forming the two waters. And then you have a sulfate and a sulfate, and those are unchanged. And you have two sodiums and two sodiums, and those are unchanged. So in the ionic equation, I'm going to leave out the spectator ions, and this becomes 2H plus aqueous plus 2OH minus aqueous, yielding 2 molecules of liquid water. Okay, so those are the steps for forming the ME, the CIE, and the NIE. Okay, next slide. Now what we're doing is we're going to be looking at combining acetic acid with potassium hydroxide. And this is going to be a neutralization reaction. So let's go ahead and start this. First of all, we have aqueous solutions of acetic acid, which we know from before is HC2H3O2. And it's a proton on our acetate, and it's listed as aqueous. And you know what? I'm going to go ahead and start this in a slightly different place so that I have a little bit more space here. Okay, so again, we have HC2, H3O2, and it's aqueous. And we have potassium hydroxide, and that is aqueous. Okay, and then it's going to form water. And you can see here that you have one proton and one hydroxide. So that's actually perfect. So we're only going to make one water at the end, and it's liquid. And then here we have our potassium and our acetate. And so we're left with a KC2H3O2. And in order to determine that, I know from my ion list that it's potassium ions and acetate ions, and that's a 1-to-1. And because we only have one proton and one hydroxide forming one water, everything in here is just 1-to-1. So this one's actually simpler than the example that I showed you on the last slide. Now our complete ionic equation is going to be H plus acetate plus potassium ions plus hydroxide ions. Okay. And that is going to yield water. And then this is aqueous as well, so it gets broken up again. And so all I've done, just as a review in my complete ionic equation, is I've broken up everything that needs to is aqueous. And I can see I have H plus and OH minus forming H2O. And the potassium and acetate ions are spectator ions. So our net ionic equation again is H plus OH minus, yielding water. And I've got all my states in here, and that's something that's very important. Okay. So the last two equations were for acid-base reactions. Now what we're going to do is we're going to look at a precipitation reaction. And in a precipitation reaction, what we do is we start with two aqueous solutions. So these are two aqueous solutions. And it's more than that. It's two aqueous ionic solutions. And what they form is they form a solid precipitate. Okay. And so here we have, in this first one, we have potassium iodide, and it's aqueous. And in this second one, we have lead to nitrate. And even though it has lead to, it's got a nitrate on it, so it is also aqueous. And when they come together over here, we are left with water surrounded by these solid, sorry, not surrounded by the solid lead to iodide. Okay. And that's what we're left here in the kind of these purpley ones. Okay. And all right, so let's take a look at what that reaction is. So this is the reaction from the previous slide. And in this one, I've always gotten this one written out, but we have, this is our lead 2 nitrate. And because of the nitrate, it's aqueous. And then we have our potassium iodide. And it is going to form a lead 2 iodide as our product. And that's our solid right here. Okay. And when we break those up, or we can see with our so first of all, we have this, the nitrate is here and the lead 2 is here. Okay, and this is already balanced. And our potassium is here and our iodine is here. And then our lead iodide stays solid because it doesn't change. And the potassium is here and the nitrate is here. And then what we're left with is we're left with our lead and our iodine forming our lead iodide. That just doesn't change. Okay, so that is the precipitation reaction from lead 2 nitrate and aqueous potassium iodide. Okay, so now let's take a look at one from the beginning. We have aqueous sodium carbonate and barium chloride, and we're going to combine them. So before we, and here it's telling you the barium carbonate, but let's walk through what would happen if we're not given that piece of information. Okay, so first of all, we have sodium carbonate. So that's Na plus and CO3, 2 minus. And these come together to form Na2CO3. And because of the sodium, we know that it's aqueous. And now we have the barium, Ba2 plus, barium chloride, Ba, and then Cl minus. Okay, and we're going to go ahead and take a look again at our ion, our solubility rules, and we can see that in rule 3, chlorides tend to be soluble, but they do not. All right. Sorry, I was interrupted there for a moment. Okay, so now we have our barium and chloride, and we can see from our rule 3 that chloride ions tend to be soluble, even with barium. Okay, so we're going to bring this together and we're going to get BaCl2, and that's aqueous. All right, now what we do is we take a look here. We know that our sodium is going to be soluble. And we know that chloride is usually soluble as well. So now let's see what happens when we combine our barium and our carbonate. And so I'm going to pull out my lists here. And I see that according to rule 6, carbonates are only slightly soluble. And so this is going to be my insoluble precipitate. Okay, so now I can bring that together and say, okay, well, that means, and they're both 2s, so we have a BaCO3, and it's a solid. Okay, and then we take our sodium and our chlorine and we put those together, NaCl, and it's aqueous. Okay, so now what we need to do is we need to balance this. So here we see that we have 2 sodiums and 2 chlorines on the reactant side. So we're just going to put a 2 here, and then we check. We have 2 sodiums and 2 sodiums, and 1 carbonate and 1 carbonate, and 1 barium and 1 barium. And actually here I can show this. So I have 1 barium and 1 barium, and then I have 1 carbonate and 1 carbonate. And we have 2 sodiums here and 2 sodiums here. And then last we have 2 chlorines. Oh, and That's okay. And 2 chlorines like that. Okay. So that's excellent. We know that we're balanced. So now we come here and we write our complete ionic equation. So I have 2 sodium ions and 1 carbonate ion and 1 barium ion and 2 chlorine ions or chloride ions. Okay. Now my solid stays put together, my barium carbonate, and it's a complete ionic. So I break this up and I have 2 sodium ions and 2 chloride ions. Okay. And now you can see that you have a carbonate and a barium forming your barium carbonate. And we leave out our spectator ions just like we did in our acids and bases. And we can rewrite this to say that barium ions and carbonate ions yield barium carbonate as a solid precipitate. Okay. Excellent. All right, now let's take a look at Avogadro's number. Avogadro's number, or the mole, is basically a number sort of like a dozen is 12. So we can use that for other things as well. And where it comes from, people are always curious, like, where'd they get this? Well, what they did is they took pure carbon 12. And remember, carbon 12 contains 6 protons and 6 neutrons. So they took exactly 12 grams or 12 grams of pure carbon 12, and they found that that had 6.022 times 10 to the 23rd carbon atoms in it. So they decided to call this number Avogadro's number, or a mole. So 1 mole of anything is 6.022 times 10 to the 23rd units. You could have a mole of atoms, you could have a mole of molecules, you could have a mole of paper clips, you could have a mole of ions, whatever. It doesn't matter. Just like you can have a dozen eggs and you can have a dozen donuts, the same type of thing. And then where this all comes from then is that we say 1 mole of carbon has 6.022 times 10 to the 23rd carbon atoms. And it weighs, though, because it's that weighted average that we learned about in the last chapter, it weighs 12.011 grams of carbon. And this is the mass number on the periodic table. Okay, so if you don't have the periodic table out right now, go grab it. Okay, so now let's take a look at the concept of some balanced chemical reactions. So we always have to balance chemical reactions, which I've sort of been showing you all along, and now we're going to do just a little bit more of it. So balanced chemical reactions provide stoichiometric ratios. So you're going to see what this is in a bit, between reactants and products. So here in this very first one, it tells us that if you have 2 molecules of hydrogen, it will react with 1 molecule of oxygen to form 2 molecules of water. Okay, so we have hydrogen, oxygen to water. Our ratios for that are 2 to 1 to 2. Okay, so that means that you could also have 4 to 2 to 4. If you so basically you just have to keep that ratio the same. So interestingly enough, you could go super crazy and you could say, okay, well then, since it's 2 hydrogens to 1 oxygen, to 2 waters, and actually this should be an H2 and an O2, to 2 waters. Okay, let's say that you have 7.68 moles of hydrogen and it's a 2-to-1 ratio, then that means you'd have half that, or 3.84 moles of your oxygen. So 7.68 moles of hydrogen, 3.84 moles of oxygen will combine together to make 7.68 moles of water. Okay, you just have to keep that ratio intact. No, we can't really count moles. That doesn't work. So what we need to do is we need to find a molar mass. So in order to find a molar mass, sorry, grabbing my own periodic table, then you look here on the periodic table. Okay, so let's take a look at how to do these calculations. So first of all, let's look at hydrogen. Now, hydrogen has 2 hydrogen units. So that means that it is going to be 2 times 1.008, okay, which means that H2 has a molar mass of 2.016 grams per mole. Now, diatomic oxygen here has 2 oxygens, and you'll find from the periodic table that that means you have 2 times the molar mass of oxygen, which you found on the periodic table of 15.999, okay, which means that oxygen will have a molar mass of 31.998 grams per mole. So again, these are, you find these values, sometimes people are confused, you're going to find this value. This is the mass of oxygen on our periodic table. Okay. And so now we have our sodium chloride, and this is just going to be a tiny bit different. So we have 1 sodium, and that means that we only have 1 of these, and that's 22.990. And we have 1 chlorine, and chlorine is 35.45. So I add these together, okay, and I get 58.44. And that means that sodium chloride is 58.44 grams per mole. All right, so now let's take a look at our water. Now we have 2 hydrogens. And so from the periodic table, that means that we have 2 times 1.008. Oh, 8. Okay. Which gives us that 2.016. And we have 1 oxygen, which is 15.999. Okay. And that's going to give us a molar mass of 18.015 grams per mole for water. Okay, now let's look at a really big one here. We've got lead to phosphate. Okay, so we have 2 leads. Okay. Oop, goodness. I see that I have an error here on the slide. So let me change that real quick, make sure that you change it as well. And this should be a 3, and this should be a 2. There, you change that as well, if it's not already changed on your sheet. Okay, now I have 3 units of lead, and so that is 3 times 207.2. Now see, PO42, that means that I have 2 units of phosphorus, so that's going to be 2 times 30.974. And 2 times 4 are 8 units of oxygen, which is 8 times 15.999. Okay, So let's go ahead and we'll do this a little bit more. So we have 3 times 207.4, which is 3 times 207.4. So you should be doing, and again, this is a great time to be pausing the video and doing this work yourself. 2 grams. And then we have 30.974 times 2, okay, which gives us 61.948 grams, and 15.999 times 8, which gives us a 127.992. And when we add all of those up, I'll put it up here, that means that the molar mass of my lead 3 phosphate, when I add these all together, is going to be 811.54 grams per mole. Okay, so now let's take a look at our acetic acid over here. And in our acetic acid, we have 4 hydrogens and 2 carbons and 2 oxygens. So that means that our hydrogen is 4 times 1.008, and our carbon is 2 times 12.011, and our oxygen is 2 times 15.999. Okay, why don't you pause the video there and calculate that? And now hopefully you paused it and you calculated it, and what you got for that is that the molar mass of acetic acid is 60.052 grams per mole. All right, so here are our molar masses. All right, so now let's do some calculations using our molar mass. Okay, and so we have 300 grams of nitroglycerin, and we want to know the molar mass of our compound. So we have 7 carbons, so that's 7 times 12.011. This is just another way of doing that. This might help you with your calculators. And then we have 5 hydrogens, so 5 times 1.008. And 3 nitrogens, 3 times 14.007. And 6 oxygens. So 6 times 15.999. Again, go ahead and pause your video and work on this calculation. And out of that, you should get 227.132. And the units on molar mass are grams per mole. Now we want to go from grams to moles. And so we're going to set up a conversion basically using this grams per mole. And so here we have, you can see this 300 grams of our compound up above. And so we start with that as our given, 300 grams of C7H5N3O6. Now, because we have grams on the bottom, top over here, we need grams on the bottom here, and we have 227.132 grams for every mole. Okay, that means we're dividing this. So we have 300 divided by 227.132. Okay. And we can have 4 significant figures here. We're right back to that 1, 2, 3, 4 significant figures. And that means that our final answer, our calculator will give us 1.320811785. If we can have 4 significant figures, this converts to 1.321, and your units for this are moles. So Avogadro's number functions like a unit conversion between moles and number of particles. So moles and atoms or moles and molecules. Okay, since 1 mole of anything equals 6.022 times 10 to the 23rd units of that thing. So remember we had many molecules of nitroglycerin. Well, what we're going to do is you start with your moles. So on the previous problem, we saw that there were 1.321 moles of our nitroglycerin. And we know that in 1 mole, we have 6.022 times 10 to the 23rd molecules. Okay. We can keep our 4 significant figures. And so this becomes 7.954 times 10 to the 23rd. And that's molecules of our nitroglycerin. That's C7H5N3O6. So now let's take a look at another one. We have glutamic acid here, and we have a 245.3 gram sample of this compound. Okay. And we want to know how many moles and then molecules are in the sample. So this is a really good place. Stop and think about what you're doing. Try to work it, pause the video, and then come back and see if you are correct. Okay, but here what we have is we have 245.3 grams. Okay, and what we're going to put here is the molar mass. Okay, and that is of course going to be in grams per mole. And it needs to go in the bottom. We're going to be dividing by it. Okay. And so if we have our here we have this. Okay. And this would be 5 times 12.011 for the carbon plus 9 hydrogens. So 9 times 1.008 plus 1 nitrogen, 14.007, and plus 4 oxygens. Okay. And when we calculate that through, we'll get 147.13 grams per mole. So even specifically say find the molar mass, you're going to need to find it anyway. Okay. I have 4 significant figures here. And so when I do 245.3 divided by 147.13, I'm going to get 1.667. And that is also in moles. Okay, now let's take a look at our molecules here. And so we can start with our moles, 1.667 moles. And again, when we're going from moles to molecules, then we can say, well, in every mole, we have 6.022 times 10 to the 23rd molecules. Okay. If we have 4 significant figures, that means that I will have 1.004 times 10 to the 24th molecules. Okay. I think that that is a great place to stop, and we will come back for our slide 30.